Okay everyone, let's try a quick tutorial on some summertime convection. I specifically here want to point out some of our warning strategies or things that may help you in a warning scenario during this tricky period of the summer. We deal with a lot of things as far as severe weather is concerned, forecasting and warning wise. So let's talk about the forecasting side first. A lot of times in our area we deal, especially in the months of November through May, we deal with a lot of wind shear. And our storms are highly dependent on instability and not necessarily wind shear, especially during our severe weather seasons. So a lot of times we hang out on this end of the scale up here where the increasing wind shear is important. So we're up here somewhere, okay? We're either an organized situation where the instability is weak or strong. So we're somewhere flip-flopping here. A lot of times, most of the time, we deal with the fact that we have higher wind shear and not enough instability. But again, what you have to realize about the atmosphere and what's important in a forecasting mode is that we are constantly dealing with this balance, finding the perfect balance between the two. Okay, and it's always going to be tricky because with the increased wind shear, it doesn't take a lot of instability to get things organized and get severe weather for our area. Summertime, let's transform that now to June, July, and August. We have exactly the opposite problem. We always have instability, have tons of moisture, tons of heat, obviously, in those months, and we deal with a decreasing wind shear scenario. So a lot of times we're in this category down here where it's unorganized, obviously, and we still have maintained these strong storms because of this increased instability. The challenge is, are there situations where you don't have a lot of wind shear, but let's say you have just enough? So again, it's all about finding that balance. With the more instability you have, it doesn't take a lot of wind shear to get things organized and get things going. And a quick example of that is northwest flow. So if you have northwest flow, a lot of times that will increase your vertical wind shear just enough to get things organized, and you must be careful in those situations because with all the instability that's already present in those months, just because of the obviously the diurnal heating, you can really get things going and going very quickly. So again, it's all about finding the balance and what is that perfect balance that we're looking for. I pulled this sounding from this week, and you can quickly see that exactly what I'm talking about here. This is a typical profile for the summertime. There is absolutely no organization in the wind shear part of the sounding. However, if you look at this sounding in general, you can see one thing that's very important about it, and that is it's moisture rich. In other words, the dew point line and the temperature line are almost on top of each other for the entire profile. If you modified this sounding and you sort of lifted it for the afternoon, you can quickly see that there is tons of instability to deal with. However, with a sounding like this and one that's so moisture rich, it's very difficult to get severe type conditions at the surface, whether that be large hail or damaging winds. Certainly you're not going to get tornadoes out of something like this. So why is that? Well, anytime you have these moisture laden updrafts and downdrafts, it's just very difficult to get a damaging cold pool at the surface. All right, so 9 times out of 10 in the summertime, yes, you will get strong storms. Almost all thunderstorms could be considered strong. You will get a cold pool at the surface, and we'll go through that. But how do you determine between a damaging cold pool that needs a warning and situations where people need to take action versus the typical summer weather? Okay, let's go all the way back and look at the processes that are going on. So you have these updrafts, you have this condensation coalescing together here to form your cloud, form these heavy drops. And essentially what happens in the summertime is that, yes, you have this stronger updraft thanks to the instability, but the downdrafts start to compete with the updraft. And so it kind of cuts off your damaging cold pool and your cold pool at the surface. Yes, you will always get one as it goes toward the surface. Yes, it will extend out from the storm. But again, what we're trying to do here is understand what is the difference between summer weather and when you need a warning, the typical summer weather, and then when you need a warning. Okay? You're always going to have this winds at the surface with the summertime storms. Can't avoid it. But when does it reach 60 miles an hour? That's sort of the question that we need to deal with here. Based on the sounding that we saw before in a moisture-rich situation, let's just kind of run through the processes here, see what happens. So you have this updraft. You're suspending the droplets, most of them above the freezing level. We know this, right? We know we're going to have ice in the storm because why? We always have lightning associated with these. So you're getting that charge differential, so you know there's plenty of ice in the storm. That's never a problem. Okay? Extends out, becomes your anvil. The whole entire process is going on right here. So as these drops above the freezing level start to coalesce and condensate together, this process starts to happen here. Eventually you're going to reach what's called a terminal velocity. In other words, the droplets are so big that the updraft can't hold them up anymore, and they begin to fall. The cooling process is taking place as well, and that's part of this. So this cold air aloft wants to come down to the ground, and it does that as the rain falls, and you get this drier air, cold pool down at the surface, and that's exactly what happens. That's why you get the winds, because once it hits the ground, it sort of splatters out in all directions, and that's exactly what the process that's going on here. So how do we differentiate that between a situation where you may need a warning, in other words, where there may be actually damage with this cold pool as it extends down to the surface? And that's when we start to work in our way toward the pulse microbursts. Okay. One big difference between the two, and you should see it right here on this sounding, is yes, you don't have a lot of wind shear again. Even though the winds are a little stronger, that's sort of meaningless in this situation. Wind shear is just not going to be important. But what you see here, especially at the mid and upper levels, is that you have a lot of dry air. So look at how that dew point line really swings out to the left as you go up in the atmosphere. So you have moisture at the surface, drier air aloft. And what that does is once you start to lift these parcels and introduce moisture into the upper levels, you can steepen those lap straits very quickly. All right. So as those lap straits start to steepen, you'll get this upper level instability, potential instability there, and it really invigorates your updraft even more. However, there's another important process that's going on as well. Let me show you that. Same kind of situation here. You have this updraft that suspends these ice and supercooled droplets above the freezing level. But again, and the important part of this is that you have this drier and stable air outside of the storm. Okay? And what does that do? That acts to start to evaporate the droplets. So once those droplets start to evaporate, you have this enhanced cooling effect aloft. So this, and we call it, sometimes we refer to it as downdraft cape, this process, once it gets going here, it can be very dangerous because the air is going to be cooled that much faster. Okay, think about the example I can give you is on your skin. So you have moisture on the surface of your skin. You don't normally notice it evaporating off of your skin, okay, but you may, when you start to do something that requires work and you start to sweat, you can feel that evaporative cooling effect to try to cool your body. But the real life example here is if you're in the shower and you get out and you turn that water off before you dry your skin, you can kind of feel that chilling effect. So there's that enhanced cooling from that environmental air evaporating these particles aloft. That rapidly cools the mid and upper levels of the cloud, and then that enhanced cold pool comes down to the surface. So that's really the bigger issue that's going on here, and that's what causes those winds to become severe, especially in the summertime. From a radar perspective, we can start looking at this, and one thing we talk about is the mid-altitude radial convergence signature. So I'm looking at this storm here from that sounding that I showed you earlier, and you can see at mid-altitudes, again we're scanning up into the storm, we're looking at about between 14 to 16,000 feet of the storm that's near Vestavia Hills, and you can quickly see this marked signature in the middle of the storm. It's not associated out here with the three-body scatter spike, but it's more interior here. You can even see some scatters that are moving away from the radar as well, so you can start to see that convergent pattern taking place. Okay, again, it's in the interior of the storm, about at mid altitudes, about where that dry air is. So if you know where those dry air levels are, you can start to anticipate where this is going to happen. Obviously, the radar can only see inbound and outbound velocities, so this is really taking place on all sides of the storm. So you're getting this convergence into the interior of the storm, and that's going to cause your damaging cold pool down at the surface. So again, conservation of mass kicks in, and those interior parts of that storm are starting to see that convergence from outside. In just a few minutes from then, you will see this divergent signature down at the surface, and by the time you see this, it's too late. Again, this is a very close storm. You have a very good look at it. Taking one more peek at the mid-altitude radial convergence, the Mark signature. A lot of times the three-body scatter spike will be associated with this arbitrary figure outside the storm, but the Mark signature is inside the storm here. Keep in mind too that you can have convergence aloft, and you don't necessarily have to see these outbounds, these red pixels. They could all be inbounds as well. So in other words, if you have faster inbounds that are slowing with time, that's also a convergence signature. So keep that in mind as well. So again, once that converges aloft, it has nowhere to go but down, and you'll get this damaging cold pool down at the surface. All right, from last week, we had a sounding that looked pretty suspicious, and this was from August 4th. This was the morning sounding, and again, it's not quite as radical as the one I just showed you, but take a look at this drier air that's working in the loft. And a couple things I want you to notice about it: where it starts and where it ends. Okay, so you have this moisture-rich surface level up through about halfway into the sounding, and then all of a sudden it dries out above 500 millibars. But what I want you to notice is where this is taking place. So over here, we've already got the minus 20 and minus 30 levels. So I'll just kind of put in the minus 10 as well, because we focus on that critical hail growth and ice growth zone between minus 10 and minus 30. And you can see it's right here in this dry air sector. This is an immediate clue that you need to watch the storm very carefully that afternoon, because these kind of processes can be happening. So anywhere in this hail or ice growth zone where you have this coinciding dry air becomes very dangerous. And sure enough, that afternoon, there wasn't a lot of storms to deal with, but sure enough, that afternoon we had that situation. And again, it's almost impossible to warn for a situation like this, but if you have those clues from the environment, you can apply them to your warning strategies here. So I'm taking a look at this storm that's near Gadsden, in between Gadsden and Rainbow City, and you can see quickly those LSRs pop up, but there's nothing unusual about this storm. You don't see really an enhancement of DBZ. It does go above 60, but just barely. Taking a look at the upper levels, again, where we looked in that zone where the dry air is taking place, again, very difficult to tell. You're so far away from the radar in these situations that you can't really see a marked signature. And there's not really even an enhancement of ice or what you would consider to be ice accumulation in this level. So a couple scans here where this drier air is quickly evaporating at mid-levels really doesn't offer any clues as to what's really happening. Only a few pixels above 60. So in this particular case, you don't even have a real chance to get a warning out. Again, going back to the sounding, look at where the dry air is. Look at what happens here at the surface now. So I've animated the surface loop of the velocities. You really don't even have a clue until you get the phone call that there's been damage up there. So again, there are going to be times when we really don't even have a chance. If you were to warn on a storm that looked like this, you would be putting out warnings all day, every day, and alerting a lot of people for nothing. This just happened to be one that we had to take on the chin a little bit because, again, that drier air aloft has evaporated those drops, and then you can see what the damaging cold pool does at the surface. So sometimes there are going to be situations where it's almost impossible to put out warnings for. But again, challenge yourself to know the environment, to understand exactly what's happening out there, and then that may give you some clues as to what you need to be watching for. The last summer tip I will give you is watch the VIL product itself. Okay, I would never advocate obviously using VIL in the warnings as a warning tool. VIL of the day and those kind of things are pretty much outdated. Hopefully you don't do anything like that. But what VIL can do is provide you clues as to where you have strengthening cores aloft. So in this situation here, there may be a storm down here near Prattville I need to take a look at. Obviously the one up near Gadsden. These can start to offer clues in a complex scenario where you're trying to balance 4 dedicated radars that you need to take a look at these 2 storms. So that could be a clue for you and maybe be a good guide and help you kind of prioritize what you need to be monitoring and looking at. Okay, that's it for this video. Hopefully you got something out of it, and we'll see you next time.